Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stacks series.
It is so wonderful to be here today. We have a seriously massive stack of research to get through.
Today, we are exploring the mechanics of intelligence, scaling laws, complexity, and the human edge.
Yeah, this is one of those topics that feels like we are basically peering under the hood of reality itself. Or at least the mathematical reality of how minds actually work.
Exactly, both biological and digital. And I want to set the stage for you listening with a fundamental question, one that I think anyone who has played around with modern AI has asked themselves, even if just subconsciously.
Right. It's that nagging feeling you get.
Yeah, you type in a prompt, the machine spits out a perfect essay or a flawless block of code, and you wonder, did it actually learn that? Or is it just a really, really expensive parrot?
That is the multi-billion-dollar question right there. It is the literal difference between understanding the actual physics of throwing a curveball versus just, I don't know, memorizing where every single baseball has ever landed in the history of the sport.
Right, which is a huge distinction. And for decades in classical statistics, we thought we knew the rules. The golden rule was basically keep it simple. If you make a model too complex, it gets stupid, it overthinks, it just memorizes the data and fails spectacularly in the real world. But recently, AI has broken all those rules.
Completely shattered them.
We are building these massive, gigawatt-hungry statistical engines, and somehow defying all the old logic, they are getting smarter.
It is a total inversion of what we thought we knew about the mathematics of learning. And to be clear to you listening, we aren't just talking about lines of code today.
No.
We are talking about the mathematical laws that seem to govern intelligence itself. We are going to look at everything from the staggering energy efficiency of the human brain.
Which runs on what, a light bulb's worth of power?
About 20 watts, yeah. It's incredible. And we'll compare that to the massive scaling laws that dictate how modern data center-sized AI is built.
It's basically a clash of philosophies, biology versus silicon, evolution versus engineering.
Interesting. So to keep us on track today, because this is a truly massive topic, I've mapped out a bit of a roadmap for our discussion.
Let's hear the plan.
We're going to break this exploration down into 4 distinct parts. First up, we have the foundations. This is the classical stuff, what we think we know about learning, bias, variance, and measuring complexity.
So the old rules.
The old rules, exactly. Then we move to the active debate. This is where the science currently disagrees. We'll look at this totally strange phenomenon called double descent.
Where making a model bigger makes it worse and then suddenly better.
You got it. Which shouldn't happen according to the old theories.
I love it when the data just flat out contradicts the theory.
Well, it's the best part of science. Then part 3 is frontiers. We'll talk about the Chinchilla Scaling Laws, which fundamentally changed how every single AI company builds their models. And we'll get into the new reasoning era we are entering right now.
And wrapping it up.
Finally, part 4 is implications. We will compare that human efficiency we mentioned against the machine's sheer brute force and ask what that actually means for the future of intelligence.
Okay, I am ready to unpack this. I want to start with part 1, the foundations. You mentioned the old rules. Now, in my head, when I think of learning, I just think of practice. You do something enough times, you get good at it. But mathematically, how do we actually define the struggle to learn?
Well, in the classical view, everything revolves around this constant tug of war. We call it the bias-variance trade-off.
I've definitely heard this term thrown around in tech circles, but let's really pin it down for the audience. What exactly are we trading off here?
Okay, imagine you were trying to find a pattern in a super messy scattering of dots on a graph. You basically have 2 main ways you can mess it up.
Okay.
The first way is bias.
Okay.
Bias is when you make erroneous, overly simple assumptions. It's when you come to the data with a really rigid mind.
Well,
say you try to fit a highly complex, wavy curve using just a straight wooden ruler.
so you're oversimplifying reality. You see a complex situation, but you only have a simple tool, so you just force it to fit. Like assuming every problem can be solved with a hammer.
Exactly. You are underfitting the reality.
Yeah.
You are too rigid. That's what we call high bias.
Makes sense. And the other side of the tug of war.
The other side is variance. This is when your model is way too sensitive. It's neurotic. Imagine you are connecting the dots on that same graph, but you are literally connecting every single dot.
Including the random noise.
Including the noise, the errors, the places where your hand slipped while drawing. You are zigzagging everywhere.
So you're hallucinating a strict pattern where there really isn't one just because you're obsessed with every tiny random detail.
Yes, that is overfitting. High variance means if I gave you a slightly different set of dots from the exact same source, your zigzag drawing would look completely different. It's unstable.
Ah, I see.
So the trade-off is that usually, if you reduce bias by making your model more flexible, you accidentally increase variance. And if you reduce variance by stiffening your model, you increase bias.
You're always trying to find that Goldilocks zone, not too rigid, not too chaotic.
That is the absolute sweet spot. But I found a really wonderful analogy in our sources from statistical learning theory that explains this concept as the approximation generalization trade-off. It uses the story of a recommendation letter.
Oh, I like a good real-world analogy. Lay it on me.
So imagine you are sitting in your office, you need an old letter of recommendation you wrote years ago to use as a template for a new colleague. You know it's on your computer somewhere.
I have definitely been there, staring into the digital abyss of my own hard drive.
All right, so you basically have a choice. Option A, you just write a new letter from scratch. This is like a high bias, simple model. It's easy to do, you know you can do it, but it might be a bit generic. It's a rough approximation.
To whom it may concern, Bob is great. Hire Bob.
Exactly. Simple, low variance, high bias. Now, option B is you literally tear your hard drive apart looking for that specific, perfect old file. You search through hidden backups, ancient emails, zip folders from 3 laptops ago.
That sounds like a nightmare, and that's high complexity, high variance.
Exactly. Option B is high variance. You're searching through a massive, complex file system. But the core problem is, do you actually have the resources to find it? The time, the memory, the patience.
So the fundamental problem isn't, does the file exist? It's, can I find it with the tools I have right now?
Precisely. Learning is about matching the model complexity to your actual data resources, not just the complexity of the problem itself.
That is a crucial distinction.
Right. If you only have 2 data points, say you've only met Bob twice at the water cooler, a simple generic note is actually better than trying to write a complex, multi-page biography.
Because if I try to write a biography based on 2 brief meetings, I'm just making stuff up. I'm overfitting the tiny amount of data I have.
You are hallucinating details. It's exactly like trying to find that specific recommendation letter when you don't even remember the file name or the year. You're honestly better off just writing the simple note.
So in this classical world, we obviously need to measure this complexity. We need to know how hard it is to find the letter, or how dangerously complex our model is getting. How do statisticians actually measure that?
There are a few heavy-hitting metrics they rely on. One that I find absolutely fascinating, and it honestly sounds like a villain from a James Bond movie, is Rademacher complexity.
Rademacher. Mr. Bond, you cannot escape my Rademacher trap.
It really does sound like that.
Right.
But it's actually entirely about coin flips.
Coin flips. Wait, how do we use coin flips to measure artificial intelligence?
It measures how well a model can fit pure random noise. Imagine I give you a massive data set of images, but instead of labeling them correctly as cat or dog, I just flip a coin to decide the label for every single picture.
So heads is cat, tails is dog, but it has nothing to do with the actual picture.
Exactly. It is pure noise. There is zero actual pattern to find. Now, I tell your AI model, hey, learn this data set. If your model is complex enough, if it has a wildly high Rademacher complexity, it can actually, quote-unquote, learn that noise. It can memorize the exact sequence of thousands of random coin flips perfectly.
Which is terrible, right? Because there's literally nothing of value to learn. It's just random.
Exactly. If your model correlates perfectly with the Rademacher variables, which are those random coin flips, it means your model is dangerously powerful for its own good. It's just rote memorizing. We want a model that utterly fails to predict coin flips, but succeeds at predicting real, actual structure in the world.
That is such a counterintuitive way to test intelligence. You test its power by seeing if it fails at learning absolute nonsense.
It's often called the ghost sample method. You compare how it handles real data versus ghost data. But there is another metric, perhaps a bit more famous, called the VC dimension.
Vapnik-Chervenenkis.
Oh, you've been practicing your pronunciations, yes. The VC dimension measures the shattering capacity of a model.
Shattering, like dropping a pane of glass.
In a geometric way, yes. It asks a theoretical question. What is the absolutely largest set of points that your model can perfectly classify in all possible ways?
Can you visualize that for me?
Sure. If I give you 3 random points drawn on a piece of paper, can your model draw a straight line to separate them, no matter which ones I decide to label positive or negative?
So if I label the top 2 positive and the bottom 1 negative, can I draw a dividing line? Yes. If I swap them around, positive, negative, can I Dilgrah line, yes.
Exactly. If your model can do that for every single possible combination of positive and negative labels for those points, your model shatters those points.
And the more points you can mathematically shatter, the more inherently complex your model is.
Correct. And these metrics, both Rademacher and VC dimension, they are crucial because they give us these theoretical bounds. They basically tell the engineer, look, with this specific amount of data and a model of this exact VC dimension, I guarantee your real-world error will be no worse than X.
So it's like a mathematical safety net. It bounds the maximum risk you're taking.
It is. We even have mathematical laws like the McDiarmid inequality, which helps bound the difference between the error you see during training in the lab and the true error you'll inevitably see out in the chaotic real world. It's all about creating guarantees.
But, and I feel like there is a huge, but coming here, this all sounds very pristine and theoretical. Out in the messy real world, especially with things like reinforcement learning or running a massive automated warehouse, does this neat math actually hold up?
This brings us to a really crucial distinction in the research that often gets entirely muddied by people: the difference between sample complexity and sample efficiency.
I will fully admit I've used those two interchangeably in the past, like just how much data do I need?
Most people do, honestly. But in the sources, specifically when looking at reinforcement learning contexts, they are fundamentally different beasts. Sample complexity is the purely theoretical number. It's the rigid math we just talked about.
How many samples do you need to mathematically guarantee you are near optimal?
Right. That's the McDiarmid stuff, the absolute speed limit sign. But sample efficiency, that is practical. That's engineering reality. It asks, how much data does this specific messy algorithm actually need to start working decently well right now?
So one is a rigid mathematical limit on a chalkboard. The other is an engineering reality in a data center.
Exactly. We have this really great example from an ArcSiv paper in our stack today about inventory control, specifically something called base stock policies.
Inventory control, like an algorithm managing stock at a massive grocery store chain.
Yes, perfect example. Imagine you are managing the stock for a giant national retailer. You have different policies or algorithms for deciding exactly when to reorder toilet paper or cereal.
Okay, follow.
The paper mathematically proves that different policies learn at vastly different speeds, even when fed the exact same data. Some policies have error rates that shrink at a nice, predictable rate of 1 over the square root of n.
Where n is the amount of data. That sounds like a pretty standard statistical rate.
It is. But other policies are much, much slower. Their error rates involve logarithms of the time horizon. The core takeaway here is that the mathematical structure of your policy, how you inherently decide to make decisions, literally changes how fast the machine can learn from the world.
So it's not just about how much data you throw at the problem. It's deeply about how your model is architecturally built to consume and digest that data. It's like the metabolic rate of the algorithm.
That is a fantastic way to put it, the metabolism of the algorithm. And this leads us directly into part 2 of our discussion, the active debate. Because, Andrew, everything I just spent the last 10 minutes telling you about keeping models simple, about bias variance trade-offs, about not shattering too many points.
Don't tell me.
Modern deep learning is basically ignoring absolutely all of it.
And this is the famous double descent mystery.
It is. And it is arguably the single biggest puzzle in theoretical AI right now.
So let's explain this to everyone listening because it is mind-bending. Classical theory says we have a U-shape. As complexity goes up, your error goes down because you learn, then it hits a bottom, and if you keep making it more complex, the error goes back up because you start overfitting.
That's the classic U-shape, yes. We believed that for decades. But modern researchers started noticing something incredibly weird when they were training deep neural networks.
What did they see?
They would add more parameters, pushing into the millions and billions, way past the point where the classical theory said the model should have fatally overfitted and crashed.
And what happened to the error rate?
The error went down again.
A second descent.
A double descent. If you look at the graph, it looks like a W, or almost like a jagged lightning bolt.
Okay, walk me through the chronological journey of a model here. Let's trace the graph.
Okay, let's trace it. Phase 1 is the classical regime. You're adding parameters. The model is learning the basic features of the data. The error drops beautifully. This all makes perfect sense.
Right, everyone is happy.
Then you hit the interpolation threshold. This is the peak of the middle of the W. This is the exact point where the model is just complex enough to perfectly memorize the training data.
So your training error is basically 0.
0. But your test error, how it performs on completely new, unseen data, is terrible. It is spiked. It is overfitting massively.
And historically, this is where we used to just stop. We'd look at that spike and say, whoa, turn it back, it's too complex. We've memorized the textbook, but we don't actually understand the subject matter.
Exactly. We would retreat. But in the modern regime, phase 2, researchers decided to just push through the pain. They kept going. They added more parameters. They made the model massively, almost absurdly over-parameterized.
And the graph goes down.
Suddenly, the test error starts dropping again. And not just dropping, it drops lower than it ever was in the classical phase. It gets spectacularly better.
Why? I mean, functionally, why? That makes no logical sense. If I'm already at the point where I'm memorizing random noise at the peak, why on earth does adding a billion more parameters fix my noise problem?
The leading theory right now, and I should stress it is still an active theoretical debate, is about the geometry of the feature space.
The geometry. Okay, explain that.
When you have that many parameters, billions of them, the model isn't just memorizing anymore. The sheer over-parameterization actually acts as an implicit smoothing mechanism.
Smoothing? How does adding complexity make something smoother?
Okay, imagine you have a few data points scattered on a page. A moderately complex model tries to wiggle a single line through all of them aggressively to get zero error. That wobbly, erratic line is the peak. It's terrible for predicting the next point.
Because it's too erratic.
Right. But if you give the model a billion spatial dimensions to work with, the model can suddenly find a much smoother, gentler curve that effortlessly passes through all the points without having to wiggle wildly between them. It basically finds a brilliantly simple solution that is just embedded inside a massive high-dimensional space.
That is wild to think about. It's like it has so much room to maneuver in a billion dimensions that it doesn't have to contort itself to fit the data anymore. It can just glide through the points.
That is exactly the visualization.
Yeah.
It glides. It implies that the tech mantra, bigger is better, might actually be mathematically true, provided you're willing to go big enough. You just have to survive that chaotic peak to get to the beautiful second valley.
But practically speaking, training these massive models takes forever. We can't just train a model to infinity parameters and sit around hoping we eventually hit the second valley. It costs literally millions of dollars in electricity and compute time. How do engineers actually manage this day to day?
They manage it by using a technique called early stopping.
Which honestly sounds like quitting, but I assume it's a bit more strategic than that.
It is highly strategic quitting. Basically, you constantly monitor a validation set. This is a small slice of data the model has never trained on. Even if your training error keeps dropping to zero because the model is starting to memorize, the very moment your validation error ticks upward even slightly, you instantly cut the power.
You pull the plug before it has the chance to memorize the noise. You trap it in the generalization phase.
Exactly. It's an implicit regularization technique. And to make this whole process of finding the right model efficient, they use some really clever algorithms, like one called hyperband.
Hyperband. I saw this in the notes. It sounded like a brutal survival of the fittest reality game show for AI models.
That is precisely what it is. It's fundamentally a bandit-based approach to optimization. Imagine you have 100 completely random model configurations, different sizes, different learning rates. You absolutely do not have the compute budget to train all 100 of them to completion. It would take centuries. So Hyperband runs all of them for just a very short amount of time.
But the audition phase. See who shows early promise.
Exactly. Then it ruthlessly cuts the worst performing half of the models. Just deletes them. That's the success of having. Then it takes the 50 survivors, runs them a bit longer, evaluates, cuts half again.
It just keeps narrowing the field.
Yes, it mathematically guarantees that you focus your precious compute resources only on the absolute most promising models rather than wasting gigawatts of energy training doomed models to completion.
It's brutal efficiency. And speaking of efficiency and speed, there's some very new research we need to touch on from Open Review regarding stability and convergence.
Ah, yes. This was the highly technical paper in our stack.
It is heavy math, but don't tune out, folks, because the implication of this paper is massive.
It really is. For a very long time, theoretical computer science thought there was a hard mathematical speed limit on learning. We thought the error rate of an algorithm could only drop so fast. Usually we thought it dropped at a rate proportional to 1 over n, or 1 over the square root of n.
Okay, so a linear or sublinear speed limit.
Right. But this new research, looking at systems under specific conditions, like the Polyak-Lojasiewicz condition.
Bless you.
Thank you. I practiced that one too. This research shows that under the right stability conditions, we can actually achieve convergence rates of 1 over n squared.
Translate that leap for the non-math majors listening. From 1 over n to 1 over n squared.
It means the mathematical process of learning can happen exponentially faster than we thought theoretically possible. It proves we haven't even come close to hitting the theoretical wall of algorithmic efficiency yet.
So, while everyone in Silicon Valley is obsessing over buying more physical NVIDIA chips, the mathematicians are quietly in the background figuring out how to do vastly more with the hardware we already have. The software itself is getting sharper.
Correct. We are unlocking sharper risk bounds. And that realization is a perfect, seamless segue to part 3 of our discussion, the frontiers. Because the biggest debate in the industry over the last few years hasn't actually been about math proofs. It's been about scaling laws.
The make it bigger era.
Exactly. We can really divide this recent history of AI into 2 distinct eras. Era 1 is what I call the Kaplan era, starting around 2020.
Named after Jared Kaplan, the researcher from OpenAI.
Yes. His team's paper was basically the founding manifesto for size is king. Those early scaling laws heavily suggested that parameter count, basically the physical size of the digital brain, was the primary, overwhelming driver of performance.
If you want a smarter model, just build a bigger neural network. Don't overthink it, just scale it.
And that philosophy triggered a massive arms race. That's exactly why we saw the sudden explosion of parameters. GPT-3, PaLM, all these massive monolithic models with hundreds of billions, sometimes trillions of parameters.
But looking back, they were incredibly inefficient, weren't they? They were these massive, bulging brains that had barely read any books.
They were grossly undertrained. Which brings us to Era 2, the Chinchilla era. This was 2022, published by researchers at DeepMind. And this paper changed everything overnight.
The new rule became balance is king.
Chinchilla fundamentally proved mathematically that the entire industry was doing it wrong. We were spending hundreds of millions building brains that were way too big for the actual amount of data we were feeding them.
So what did they actually find? What is the secret recipe for a perfect model?
The Chinchilla Scaling Laws established a golden ratio. They proved that to minimize your loss under a fixed compute budget, you must scale your model size and your dataset size equally.
And they gave the industry a very specific number to aim for, right?
They did. The magic number is roughly 20 tokens of data per parameter in the model.
Let's break that down so it's concrete. 20 tokens per parameter. So if I am building a 70 billion parameter model today,
you absolutely need to train it on roughly 1.4 trillion tokens of high-quality text data.
That is an unfathomable amount of reading.
It is. But the impact of that discovery was industry-altering. It meant you could build a physically smaller model, like a 70 billion parameter Chinchilla optimal model. And if you train it on enough high-quality data, it would vastly outperform a model 4 times its size that was trained using the old Kaplan ratio.
This totally explains why we are seeing all these incredibly powerful open weights models right now, like Llama, that can actually run on consumer hardware or high-end laptops that aren't bigger than the older models. They're just vastly better read. They are Chinchilla optimal.
Exactly. It completely shifted the industry bottleneck.
Yeah.
It went from how many GPUs can we possibly buy to where on earth do we find enough high-quality human-generated text to feed this golden ratio.
But Renee, when we scale these things up to these massive trillion token regimes, are they just getting statistically better at predicting the next word, or is the actual internal architectural structure of the model fundamentally changing?
This is where we get into a field called mechanistic interpretability. We are actively trying to peek inside the black box to see what's happening. And the sources show that something genuinely fascinating happens at scale.
Emergent structure, like it builds its own anatomy.
Yes. They call it emergent modularization. As these models scale up and train on vast data, they naturally develop what researchers call interpretable subcircuits.
Subcircuits? Like the model spontaneously creates a specific part of its brain for a specific type of task.
Exactly that. Researchers probed these scaled models and found specialized output nodes. They found specific attention heads and multi-layer perceptrons that just independently took responsibility for very specific tasks. For example, they found a circuit that only activates to solve multiple choice questions.
Wait, so nobody programmed a multiple choice solver into the code. The model just realized it was doing a lot of multiple choice questions and evolved a specific brain region to handle it efficiently.
It evolved it entirely on its own, because statistically that was the most efficient way to minimize error. They also found these structures called low-rank subspaces. The model encodes complex features into very simple three-dimensional spaces inside its network, acting like a counting or enumeration mechanism. It's literally building specialized cognitive tools inside its own mind.
That sounds absolutely incredible. But knowing AI, is there a catch? Does it always work perfectly?
There is always a catch. This beautiful interpretability, these neat little subcircuits, they work really well for canonical knowledge, facts that are consistently true in the training data. But when researchers purposefully randomized the labels...
When they lied to the model?
Yes, when they fitted deliberate nonsense to see what would happen, the elegant interpretability completely broke down. The internal mechanisms became tangled and confused. They call it becoming entangled.
So the model is highly organized and modular when it's learning the truth, but its brain architecture literally becomes a messy bowl of spaghetti when it's hallucinating or trying to process nonsense.
It strongly suggests that the internal physical structure of the model's intelligence is deeply dependent on the coherence of the data it consumes. If you feed it garbage, its brain architecture literally becomes garbage.
Garbage in, garbage out, but now we can actually see the garbage actively destroying the geometry of the mind.
Exactly.
Yeah.
And seeing that architecture leads us to the next massive shift, because we are now moving past just scaling the training phase. We are officially entering the reasoning era.
This is the big System 1 versus System 2 distinction that's everywhere right now.
It is the defining shift of the current frontier. Up until very recently, basically all standard large language models were System 1 thinkers. If you think back to Daniel Kahneman's psychological framework.
Right. System 1 is fast, instinctive, automatic pattern matching.
Exactly. I ask a question, it instantly blurts out the statistically most likely answer.
And that's exactly why they hallucinate so confidently. They aren't fact-checking, they're just predicting the next likely syllable based on vibes and statistics.
Precisely. But System 2 is deliberative. It's slow. It's highly logical. It requires actual thinking time to break a problem down.
And this is where the new concept of inference compute scaling comes into play. I saw a quote in our research stack today that honestly blew my mind. The quote was, 20 seconds of thinking is worth 100,000 times more data.
It is a staggering claim to make. But it fundamentally suggests that instead of just endlessly making the initial pre-training process bigger and bigger, we should let the model talk to itself during the actual answering phase. Let it think for longer before it shows you the final answer. We call this inference scaling.
This is the chain of thought process we see in newer models.
Yes. The performance of the model scales drastically with how long you allow it to think. It's the exact difference between a human answering a complex riddle instantly with the first thing that pops into their head versus sitting silently with a pen and paper for 5 minutes working it out.
So the true intelligence isn't just stored in the static weights and connections of the network. It's dynamically generated in the process of reasoning over time.
Exactly. The process is the intelligence.
This feels like a massive bridge to how humans actually think and problem solve, which brings us perfectly to part 4. Implications. Because for all this talk of gigawatt scaling and inference compute, you and I are sitting here having this complex philosophical debate, and our brains are basically running on half a turkey sandwich and a cup of coffee.
The energy disparity is honestly staggering when you put it in perspective. The human brain operates on roughly 20 watts of power. As we said, that is a dim refrigerator light bulb.
And we do that while continuously learning over an entire lifespan. I didn't stop training in 2023 when a dataset cutoff happened.
Right, you are constantly updating your weights. Meanwhile, training just one of these frontier AI models requires gigawatt hours of energy. We're talking about the dedicated energy consumption of small cities for months at a time.
And the data efficiency is just as mismatched. You mentioned earlier that machines need millions, billions of examples.
Billions. If I want to teach a human child what a cat is, I don't need to show them a million photos. I point to a cat in the living room maybe 3 times. I say, that's a cat. Done. The child generalizes the concept instantly.
Extreme few-shot learning.
Exactly. Because humans use prior knowledge. We use physical context to build causal mental models of why things happen. We intuitively understand physics, gravity, biology.
Whereas the machine is just using sheer brute force.
Complete statistical brute force. It is blindly looking for numerical correlations in massive matrices of pixels or text. It has no conceptual understanding of what a cat actually is in the physical world.
And because of that fundamental difference in approach, this leads to entirely different shapes of learning. Our sources beautifully describe the 4 shapes of learning.
I really love these visualizations because they apply to both biological and artificial systems depending on the task.
Walk us through these 4 curves.
First, you have the curve of diminishing returns. This is a very fast start, rapid improvement, but then it severely slows down and flattens out.
Give me a real-world example.
It's like learning a very simple mobile game on your phone. You figure out the mechanics instantly, you get pretty good in 10 minutes, and then you just plateau. You aren't going to get exponentially better at Flappy Bird after year 5.
Okay, that makes sense. Diminishing returns. What's next?
Then you have the opposite, increasing returns. This starts painfully slow. You are struggling, you don't get it, the error rate is high, and then suddenly, boom, an aha moment. The curve shoots straight up.
Like learning a complex skill.
Exactly like learning to write code or playing a musical instrument. It sounds terrible for months, and then suddenly your brain wires the connection and you are playing songs.
That breakthrough moment is so satisfying. Okay, curve 3.
The third is the S-curve, or sigmoid curve. It's a combination. Slow start as you learn the basics, then a period of incredibly rapid, steep improvement, and finally a leveling off into a plateau of mastery.
I'd imagine that's like learning to drive a car professionally. Slow at first, then you get confident quickly, but eventually you hit a hard physical limit of your reaction times.
Perfect example. And the fourth curve,
The dreaded fourth curve.
the plateau. This is flat from the start. You practice, you expend energy, but there is absolutely zero visible improvement on the graph.
The stuck phase. I feel that personally when I try to learn French.
We all have our plateaus,
Mm-hmm.
but what's genuinely fascinating is mapping these mathematical learning curves to the classic psychological stages of competence.
Oh, I remember this framework from a psychology elective in college. The 4 stages of competence.
Let's do an exercise.
Mm-hmm.
You map the psychological stages, and I will map the AI model training journey to match it.
Okay, challenge accepted. Stage 1 in human psychology is unconscious incompetence. You don't know how to do the thing, and you don't even know what you don't know about it. You are blissfully unaware.
In AI, this is a randomly initialized neural network at epoch 0. It knows absolutely nothing. Its outputs are pure random noise. It doesn't even know what language is yet.
Spot on. Stage 2 is conscious incompetence. This is the painful phase. You now realize exactly how bad you are. You see the massive gap between you and the experts. It's high frustration.
For the machine, this is early stage pre-training. The loss function is astronomically high. The backpropagation gradients are basically screaming error at every layer of the network. It's flailing to find direction.
Stage 3 is conscious competence. You can finally do the task successfully, but it requires heavy, active concentration. You have to think through every single step deliberately.
And this is exactly where we are right now with current System 2 AI, the reasoning models. They can finally solve the complex PhD math problem, but they have to think out loud step by step, generating long chain of thought tokens. It is computationally effortful and slow.
Which brings us to the final goal. Stage 4 is unconscious competence, pure muscle memory. It becomes second nature. You do it perfectly without even thinking.
This is the holy grail for efficient AI. The goal of current research is to take that slow, expensive System 2 reasoning process and somehow distill it back into a fast, cheap System 1 instinct to make deep reasoning computationally effortless.
But Renee, there was a very serious warning in the sources about this exact process. They called it a complexity cliff.
Yes, this is the dark side of our obsession with reasoning models. Recent research strongly suggests that these logical step-by-step models do not degrade gracefully.
What does that mean, practically, not degrading gracefully?
Well, think of a standard older AI model. If it doesn't know the exact answer, it might just give you a slightly wrong, blurry answer. It's a bit off, but mostly harmless. It's a gradual error. But a reasoning model, because it builds a very rigid, sequential, logical chain of thought.
Like a tower of blocks.
Exactly. If just one single link in that logical chain breaks or makes a tiny error early on,
the entire tower collapses. The final answer isn't just slightly wrong, it's wildly, confidently incorrect.
it collapses entirely. It hits a complexity cliff. And the implication here is profound. As we start relying on these advanced AI systems for much harder, critical problems like real-time medical diagnoses or engineering physical structural supports for bridges.
The failures might not be little typos anymore. They might be sudden, catastrophic logic failures.
Exactly. It's a fundamental trade-off we're making. We are trading the robust, blurry generalization of the past for extreme precision today. But that precision introduces severe fragility.
That is both terrifying and utterly fascinating. It means that as these systems get objectively smarter and more capable, they might actually become much more brittle and dangerous in highly specific, unpredictable ways.
It's the paradox of complexity.
So stepping back from the math and the cliffs, where does this grand narrative actually leave us? We have humans on one side with our miraculous 20-watt efficiency, our deep causal understanding, but hard biological limits on our memory and speed. And on the other side, we have machines with their gigawatt brute force, their brittle logic chains, but seemingly infinite scaling potential.
I genuinely think the future isn't the sci-fi trope of human versus machine. The sources and the trajectory of the math itself point heavily toward human with machine.
Symbiotic relationship, a hybrid intelligence.
We humans have reached a biological plateau. We are fundamentally limited by our skull size, our processing speed, and our lifespan. We simply can't scale our biological brains up by a factor of 10.
Believe me, I've tried drinking more coffee. You cannot just add more RAM to a human head.
Exactly. But the machine has this undeniable superhuman potential to scale its sheer statistical processing power. The true synergy in the future comes from combining the machine's massive, high-dimensional statistical power with the human's highly efficient context, our common sense, and our unique ability to navigate the why of the universe.
It's the ultimate centaur model of intelligence. We provide the intent, the ethics, and the physical grounding, and they provide the raw, unlimited compute to explore the vast geometric spaces of possibility.
It is. When you trace the entire journey today, from the pure math of predicting coin flips with Rademacher's complexity to the massive physical physics of cooling giant data centers for Chinchilla models, we are really just trying to figure out how to navigate and compress the information of the universe.
And perhaps in the obsessive process of building these artificial minds and studying how they break and how they learn,
we are finally going to learn how we actually work.
That is the ultimate reflection, a mirror made of silicon. And I'll leave your listeners with one final, slightly provocative thought to mull over. If the architecture of an AI's mind physically changes based on the data we feed it, as we saw with emergent modularization, what happens when the AI becomes smart enough to start designing its own optimal learning curriculum? What kind of mind will it build for itself when we are no longer the ones choosing the textbooks?
That is a question that will define the next decade of this field.
Something to keep you all awake tonight. Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us in Patreon. And of course, you can write to us in comments if a specific topic needed to be covered would help us all to grow.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.